8.3 vector, parametric, and symmetric equations of the line in R cubed. Okay, so now we're going to go from R squared to R cubed. So in R cubed, if R naught, like the vector R naught, equals X naught, Y naught, Z naught, is determined by a point on the line, and vector M is ABC, is a direction vector of the same line, then what ends up happening is this is the vector equation of a line in R cubed. So it's going to be like the vector equation, which is like vector R equals R naught or vector R naught. This is essentially a point. This is essentially a point because it's the point joining that point in the origin. Okay, and then some plus some parameter t times the direction vector m. Okay, and t is an element of the real number system. Another way that you can write this is just another form of writing it. You don't see this as often, but you can write it as xyz in brackets and then equals, then put your point there, or it's like the direction vector r naught, x naught, y naught, z naught, plus the parameter t, abc. Again, abc being vector m. Okay, so this is a point and this is a vector. Okay, and as a recall, r naught, like vector r naught, is a vector from the origin to the point on the line. And to the point on the line, which like that point would be obviously x, y, z. Okay, and then vector m, ABC is a direction vector. Okay, so this is just showing you the setup of that. Now, parametric equations also extend to z. Okay, instead of just being x naught, y naught, is now also z naught. These three make up a point, and then ABC, so that's a comma there because it's like comma, t is an element of the real number system, but ABC is a direction vector. Okay, we can call it M, direction vector M. Okay, so again, just extends to the Z. And now, symmetric equations of a line. This is a little bit different, okay? Symmetric equations of a line are essentially the form T equals T equals T. That's essentially what we're doing here, okay? So I'm going to show you this with the parametric equations because we go from parametric equations to symmetric equations, okay? And this idea is new. So if we had x equals x naught plus TA, I would move the x naught over to isolate for t. Now we have x minus x naught equals TA, and I would divide both sides by a. So now I just get t equals x minus x naught over a. And this is that first symmetric equation. You can then further do this with the y. So we'd have y equals y naught plus tb. We bring over the y naught. We get y minus y naught equals tb. We divide both sides by b. And we can put b, t equals. So t equals y minus y naught over b. And then this t value is going to be the next t. So obviously t equals t, and then now we have y minus y naught over b as our second value. Okay, and then likewise, I'm not going to do this one, but likewise you can do it with the z, and it's going to be z minus z naught over c. Okay, all of these equal t. All of these are equivalent. Okay, and then just like the denominators, a can't be 0, b can't equal 0, and then c cannot equal 0. That's the restrictions on that. Okay, so just pretty much they have to be numbers. Okay, so just note all three of these equations depend on the others. So by knowing one equation, you'll know the others. Okay, and we'll see that in questions. So let's go ahead and start example 1. A line passes through these 2 points, A and B. So first, calculate possible direction vectors for this line. Okay, so we have two direction vectors that these could possibly make. We have AB and we have BA. Okay, let's take a look at these. So AB, if you remember direction vectors, we subtract backwards and we subtract components. Okay, we are going to end with a direction vector. That means that we're going to end with something in component form. Let's go ABC. Okay, so we're not adding these like a dot product. It's just going to be a vector. So -3 minus -1, comma, 3 minus 3, comma, -4 minus 5. Okay, so -3 minus -1 is just -2. 3 minus 3 is 0. And then -4 minus 5 is going to be -9. Now, let's do vector BA now. This time, we're going to go A minus B. Okay, we have to stay consistent as well. So, -1 minus -3, 3 minus 3, and 5 minus -4. Okay, so if we simplified this, we'd get 2, 0, 9. Okay, let's take a look at these two. What do we notice? A, B, and BA are scalar multiples of one another. By maybe the scalar -1. Okay, because we can actually conceptualize this as like, say this vector here was AB. Well, then we know that vector BA is just going to go in the opposite direction. Okay, opposite direction meaning is a scalar multiple of -1. Example 2, determine the vector and parametric equations of the line passing through these 2 points. Okay, so we pass through P and Q. So when we talk about the vector equation, if you remember, R equals vector R naught plus some parameter T times a direction vector. Okay, so we need a direction vector. Let's do PQ. Okay, which means Q minus P. -2 minus -2, comma, 4 minus 3, comma, -1 minus 5. So we have 0, comma, 1, comma, -6. And now we can go ahead and write the vector equation for this line. Okay, so for the line that passes through P and Q, we have a point. It doesn't matter if you choose to write point P or write point Q in this first, like where vector R naught is, either one. So I'm just going to pick P, but if you do Q, that's okay too. So -2, 3, 5, okay, plus some parameter T, and then we're going to bracket 0, 1, -6, because that's the direction vector. Okay, so what we want to do now with these components is we're going to write out the parametric equations. So we're going to have x equals, y equals, and z equals. So we can take this point here and we can stack these numbers, -2, 3, and 5. And then we take these points. So plus 0t, you don't actually have to leave that in, that's fine. You can just put x equals -2, okay? Plus 1t, and then minus 6t. Okay, this is a vector equation. And these are parametric equations. Okay, example 3. Show that the following vector equations are for the same line. Okay, so we have two vector equations. Okay, so we have a point on each and then the direction vector of each. Okay, so first what we want to do is we want to check, like if they're the same line, then the direction vectors are technically going to be the same. So we want to check that direction vector 1 is some scalar multiple of direction vector 2. Okay, so we're just going to call D1 negative 1, 2, and 5. Okay, and then D2 negative 2, 4, and 10. So what we'll do is we'll divide vector D2 divided by vector D1. So negative 2 over negative 1, 4 over 2, and 10 over 5. Okay, we're dividing each of these components. Okay, and we get 2 equals 2 equals 2. Okay, therefore, we can conclude that these two lines are one of two things. Okay, they're either parallel and distinct, or they're parallel and coincident. So they're either parallel in their own line or parallel in the same line. We can say, you know, I'm not going to put it there for it, that's fine. Okay, so what we want to do is we want to show, I'll just put a little note, show one point lies on the other line. Okay, so we can't work with this in vector form. So what we're going to do is we're going to write line 1 in parametric equations. Okay, so we're going to have x equals, y equals, and z equals. So the first point is negative 1, 0, 4. Let's go ahead and write that. And then we're going to say minus s plus 2s plus 5s. So what we'll do is we will take the point from line 2 and we'll sub it into line 1. And then what we're going to do is we're going to see if all three parameters equal the same thing. Okay, in other words, are we able to sub in some parameter to punch out this point? Okay, because if lines go through the same point, okay, so I think what I want to say is every single point on one line is going to go through the other. So as long as this point for negative 10, negative 21 satisfies this line with obviously the same parameter s, then these two lines are going to be the same line. Okay, so let's go. X equals 1 minus s, and this x we're going to sub in 4. Okay, I don't like working with a negative s. I'm going to bring the negative s over, and I'm going to bring the 4 over here. So I get 1 minus 4. I get s equals negative 3. Sorry, this is negative 1. Negative 1. So negative 1 minus 4, s equals negative 5. That's better. Okay, we're going to do the same thing for y. So we have y equals 0 plus 2s. Okay, this time we're going to sub in negative 10. So negative 10 equals 2s. So we have s equals negative 5. Okay, so there's some parameter s equals negative 5 that we can sub in to at least get the x and the y. But it has to satisfy all three. So let's try z. Okay, z is negative 21. So 4 plus 5s. Bring over the 4, so negative 21 minus 4 equals 5s. I get negative 25. Divide both sides by 5. And I get s equals negative 5. Okay, so we can do a little bit of a therefore statement. Since all of the s's are the same, since all parameter s are the same, And D1 is a scalar multiple of D2, vector D1, vector D2. This is the same line. Okay, B, show that the following vectors are for different lines this time. Okay, so we're going to have the same approach. Right now we have line 3 and line 4, and we have two vector equations. So let's first check the D1s and the D2. Okay, so D1 equals -1, 1, 2, and vector D2 is 1/2, -1/2, and -1. So let's go ahead and stack these on top of one another. So I tend to do, like, if one of these have bigger numbers, I tend to put the bigger numbers on top. So we can do D1 divided by D2. Okay, vector D1. So -1, -1, and 2. And let's see if those are equivalent to 1/2, -1/2, and -1. So when we divide these, we get -2 equals -2 equals -2. Okay, so yes, D1, like the direction vectors are scalar multiples of one another. So now we can test one of the points in the other equation. So taking a look at these equations, I would rather deal with the equation with no fractions. So let's write the parametric equations for this one. X equals, so I'm going to actually write them a little bit different this time just to save space. Okay, so we're going to take all of the X components, 1 and then -1L, 1 minus 1L. Then we're going to have 6 plus 1L. And then we're going to have 1 plus 2L. And let's go ahead and sub in -3, 10, and 12 and check if there's some scalar multiple, or like, sorry, some parameter L that we can sub in order to get -3, 10, 12. So we have 1 minus L. I don't like the negative L, so I'm going to bring the negative L over and we get L. I'm going to bring the -3 over and we get +3. So we get that the parameter for the first one would be L equals 4. Okay, again, what this means is that if we plug in L equals 4, so if we plug in a 4 for the L, we will get an X value of -3. Now, 10. We have 10 equals 6 plus L. Bring this one over. 10 minus 6 equals L. L equals 4. Okay, so looking good so far. We have two L's that equal 4. So again, we sub in the parameter 4. We will get -3 and 10 for sure. But we're not done. You have to make sure that 4 satisfies all three of these. Okay, parametric equations. So let's bring over the 1. I get 11 equals 2L. Divide by 2. Well, this time I get L equals 11 over 2, or in other words, 5.5. Okay, so since this is not the same line, therefore, these are not the same line because the L's are not the same. Okay, so despite the direction vectors being scalar multiples of one another, you also have to test the L. So just take note, these two lines, because they have scalar multiples of the direction vector, they're going to be at least parallel, okay? So we can say at least parallel, okay? But that's exactly what they are. Okay, so again, you're either going to get parallel and distinct, and I can quickly draw these in 2D, right? You're going to get parallel and distinct, or if one point lies on the other line, what we're going to get is the same line. So parallel but coincident. Okay, in this case, they're parallel and distinct. They're not going to have any points of intersection. Okay, symmetric equations of the line in R cubed. So symmetric equations are derived using its parametric equations. Okay, we always have to start with parametric equations. If you don't have these, then rewrite your maybe vector equation or find the parametric equations, list them out. Okay, and they're solved by actually solving for a parameter. So remember, these would be the general form for the parametric equations of a line. So we would bring over the x naught, so x minus x naught, and then we would divide by a. And we would bring over y naught. We would have y minus y naught divided by b. And then we would bring over the z naught, z minus z naught divided by c. So I kind of already showed this, so I went through it a little bit quicker here. Okay, and then A does not equal 0, B and C do not equal 0. Okay, combining these statements gives us, ready? I'm going to put it here. So x minus x naught over A equals y minus y naught over B equals z minus z naught over C. Okay, these are the symmetric equations. So example 4 asks us, write the symmetric equations of the line passing through the points A, B. So first of all, we need a direction vector. We need the direction vector, let's call it AB. So we're going to do B minus A. So 3 minus negative 1. Negative 4 minus 5, 8 minus 7. Okay, so we get 4, negative 9, 1. So let's talk about these. Let's write out the parametric equations, x equals, y equals, z equals. So we're going to have some x, y, z. It doesn't matter if you pick A or B. Let's pick A, negative 1, 5, 7. Okay, and then we're going to have, let's introduce the parameter t. Okay, so let's introduce parameter t such that t is an element of the real number system. So we're going to have this direction vector. We're going to have plus 4t, minus 9t, plus 1t. Okay, if you're not okay just looking at a point and listing them, and then just looking at a direction vector and listing it, you can go ahead and write out the vector form first, and then convert that to parametric equations. Okay, but you don't need to. So let's now write symmetric equations. So we would bring over the negative 1, and we'd get x minus 1, and then we would divide out by 4. Okay, so for the y, we would bring over the 5, y minus 5. Then we would divide out by negative 9. And for the z, we would bring over the 7 and divide out by 1. So actually, we can just write equals z minus 7. And a lot of times, solutions will put this like right in the middle. It won't be shown over 1. But you can put it over 1, and that's okay too. Okay, sorry. This negative 1, it would become plus 1. B, write the symmetric equations of the line passing through PQ. So we're going to do the same thing. PQ, we're going to find the direction vector. So remember, Q minus P, 4 minus negative 2, 3 minus 3, negative 5 minus 1. Okay, so we now have a direction vector of 6, 0, negative 6. So let's write out the parametric equations. We're going to write out a point first. Okay, I'm lazy. I don't even look past this. Let's just use a point P. -2, 3, 1. Now let's introduce the parameter s such that s is an element of the real number system. Okay, so we're going to write 6, 0, -6 with the parameter on it. So plus 6s, and then this is like plus 0s. You don't really need that here. Okay, and then minus 6s. And then all we have to do is rearrange these. So let's bring over the -2, and we get x plus 2. And we're going to divide by 6. Okay, now this is going to be y minus 3 divided by essentially 0. We're going to talk about that in a second. And we're going to have z minus 1 over -6. Okay, so when we take a look at this, we cannot write this part of the symmetric equation over 0. Okay, this is a special case. So we're going to go ahead and write the first symmetric equation like x plus 2 over 6, and then z minus 1 over -6. Okay, we're going to go ahead and do that. Then we're going to deal with this afterwards. So what essentially happens is like we can't write this normally. So because this has 0s here, we simply just write y equals 3. Okay, so you can make a note here, cannot write a symmetric equation over 0. So this is what we do instead. We basically take the parametric equation, which is y equals 3, and that's what we use. Okay, see, write the symmetric equations of the line passing through x, y. So let's find direction vector x, y. So -1 minus -1, right? Because we're going y minus x. 3 minus 2, 9 minus 5. Okay, so it's 1, 1, 4 is our direction vector. Sorry, 0, 1, 4. Okay, so let's go ahead and write out x equals, y equals, and z equals. Okay, so we have 0, 1, 4 as our direction vector, and we can pick point x or y, doesn't matter. Let's pick x. So -1, 2, 5, right? We list our point, plus, let's go m, where is m is an element of the real number system. M is going to be our parameter this time. So we have 0, 1, 4. So 0m plus 1m plus 4m. Okay, so immediately when I'm looking at this, I'm thinking this 0m, x equals -1. We're actually going to have to use that in our symmetric equation, which is totally fine. Okay, so let's just list them in order. X equals -1. And then let's list our actual symmetric equation for what else? Y and z. Okay, so y is going to be y minus 2. And it is over 1, so let's just leave that. And then equals z minus 5 over 4. And I think that it's more acceptable, and it's better form to write our symmetric equation first, then put a comma, and then list any of these, oops, I don't want to box this, any of these parametric equations after, where we would have had to divide by 0, so that doesn't work. Because we want to have this equivalence, right? Equal sign, equivalence, this equation first, and then the x equals -1.